So in this video, I want to talk about what astronomical knowledge we were able to achieve before what we would think of as modern technology like the telescope and what we think of as modern processes like the thing we today call science. We already talked about what sorts of motions and cycles are visible in the sky, so the question is, how were we able to both measure and understand these cycles before what we might call the scientific revolution that happened around the time of Galileo and Newton, 1600s or so? And what is the evidence that these observations were being made? A lot of the evidence comes from observing alignments in structures that have existed for thousands of years. I chose this example because I've been here. This is a temple called Manidra in Malta. And I went to a conference in Malta in 1999, and we went on an excursion to two of these temples. This temple is basically just a ring of stones, and there's a doorway. And the doorway is low, you kind of have to duck to go through it. But if you look opposite the doorway, on the other side, there is a little indentation, a little square hole in the wall. And it turns out that when the sun rises on the summer solstice, the shadow of this rock hits just on the one side of that square indentation. And when the sun rises on the winter solstice, the shadow of that rock hits just on the other side of that indentation. And on the on the winter solstice and summer solstice, it hits the edge. On the equinox, the sun rises directly in the center of this doorway and fully illuminates that square on the back wall. This is probably not an accident. If this doorway is exactly lined up with this hole on the other side so that during the spring and fall equinoxes, the sunrise exactly lines up with that doorway, that is intentional. And one has to recognize that building a big stone circle that exactly tracks the sunrise over the course of the year from summer solstice to fall equinox to winter solstice to spring equinox and back again requires many years of careful observation. You can't just build this stone circle and then hope it lines up, right? You have to kind of figure out where the doorway is going to be and where the hole is going to be and watch the sun for several years to make sure that those shadows are going to line up directly. It's a lot of work and effort. Why? Why would you build a big stone circle that tracks the motion of the sun? Who cares when the solar solstices and equinoxes are? Well, if you are a culture that relies on agriculture, you need to know when spring is coming, so you know when to plant the seeds. And you need to know when winter is coming, so you know to harvest the seeds before it gets done. The motions of the sun in the sky are clues, pointers to important events that an ancient culture needs to be aware of. So carefully measuring the position of the sun and the changing seasons was a life or death matter for ancient cultures. One of the most famous, way more famous than the temples in Malta, examples of a monument that is aligned with astronomical events is Stonehenge. I've been here too. It's really, if you've ever been to Stonehenge, it's kind of lame. It's like, you see pictures and it's beautiful and it looks like it's in the middle of this field. There's a highway literally like 100 feet that way. Like you pull off the side of the road and it's like, oh, there's Stonehenge. It's not in this pristine environment, and you can't go in to where the stones are now. It's all fenced off or roped off, and you can't go into the actual stone circle itself. But you probably know that the circle of stones in Stonehenge, some of the stones are lined up to point directly to sunrise on a particular day of the year. Some of the stones are lined up to line up with where the moon rises at its northernmost point and its southernmost point from that location in England. There have been hundreds of proposed alignments between certain places you stand in Stonehenge and certain risings and settings and motions of things in the sky. A lot of these are probably BS, and a lot of these are probably coincidence. If I put a big stone circle in a field anywhere on Earth, some of those rocks are going to line up with interesting stuff that happens in the sky. But certainly, the summer solstice and equinox, the positions of the moon, the rising and setting positions of some bright stars like Sirius are very clearly exhibited by the Stonehenge monument. Again, these are not stones that one person could lift, right? These are stones that took hundreds of people to move and roll across the English countryside. Imagine how many years of observation had to happen before the stones were put up in order to make sure that those stones were in exactly the right place. All around the world we find examples of this. The Maya in Central America, mostly what is now Mexico, developed some extremely accurate pre-telescopic observations of the sky. Their pyramids are aligned usually with the rising sun. Most monuments, a lot of Christian churches are aligned with the rising sun in the east. Not uncommon, but their observations of the sky go far, far beyond that. This is all before the year 1000. This is a book called the Dresden Codex. It dates from around the year 1200 and contains extremely detailed tables of the motion of the moon, the motion of Venus, the motion of Mercury. And some of these cycles that they identified, precisely measuring the cycles of Mercury and Venus, seem to be based on as much as 800 years of careful observations of the sky. So not just precise observations of the sky, but very, very long-term observations of the sky. You wouldn't be able to identify these cycles as accurately as they did without observing the sky for many, many, many years. Here's one example. The Maya calculated the length of a month. You might say, isn't a month like 30 days or 29 days? Yeah, but they really calculated the length of the month. The number of days in a lunar month they calculated to be 29.53086. The actual calculation with modern telescopes and modern technology is 29.53059. That's a difference of 1/1000th of 1%, 0.0001. Really remarkable. What needed to be done in order to do that? Very careful measurements of how many days have gone by, how many months have gone by for years and years, maybe hundreds and hundreds of years, and then dividing those two numbers by one another. The Maya were also able to predict solar and lunar eclipses. I said in another video that solar eclipses are fairly rare. If you can move around the Earth on planes and boats, you can see a solar eclipse every couple of years. But if you are stuck there in Central America, you might see an eclipse once a decade, once every 30 years, once every 50 years, which means the fact that they were able to figure out this cycle of how often solar eclipses happen meant they were taking careful records for hundreds of years. Their predictions were good thousands of years into the future. For example, in 2017, there was a total solar eclipse of the sun visible right here on the eastern coast of the United States. It was a partial eclipse here in Richmond. I actually drove down to South Carolina to see the total solar eclipse. Highly recommend it if you ever get the chance to do so. The next chance is in 2027, 2029, something like that. When we talk about solar eclipses, I'll let you know the exact number. The point being, the 2017 solar eclipse that happened here in the eastern United States was predicted by the Mayan tables of eclipse predictions from 800 years ago. If we go to Asia, if we go to China, we find that Chinese astronomers have been making detailed star maps for 3,000 years. This is a Chinese star map from the year 700. You can see right here, you can see the Big Dipper is right here. So Polaris, the North Star, is right here. Recognizable constellations and careful measurements of the positions of the stars in what we would today call the Middle East. In the ancient Islamic world, there were detailed star maps being made in the 10th and 11th centuries. Astronomical instruments like the astrolabe, which is kind of a pocket calculator for figuring out where the stars and moon are going to be on any particular night were invented in the 11th century. Islamic astronomy had a huge influence on medieval European astronomy, so much so that most of the named stars in the sky, those proper names of those stars are Arabic in origin. For example, Betelgeuse comes from Arabic. Aldebaran, Al-Natak, Al-Narath, a lot of them start with Al, like algebra. It's a common word article in Arabic. So anywhere we go in the world, we will find evidence of astronomical record keeping and astronomical knowledge. I'm not an expert in these things. There is a whole field of inquiry related to these questions. There's one called archaeoastronomy. Archaeoastronomy is simply figuring out what tools and knowledge ancient civilizations had and understanding the meaning of monuments like Stonehenge and the Malta temples. And there's ethnoastronomy, which is understanding the cultural meaning of this astronomical knowledge within these various cultures. I'm not an archaeoastronomer and I'm not an ethnoastronomer. Those fields have a lot of overlap with archaeology. They have a lot of overlap with sociology, and they are very interesting in their own right. For us, in a science class about astronomy, we are interested in this question. What's the difference between what these ancient cultures did, which was incredibly impressive and required incredible technical, observational skill, and what we today call science with a capital S? The main difference is this. There's little or no evidence that these quote-unquote pre-scientific cultures, whether it's the Maya or the people who lived in England and built Stonehenge, or the ancient Islamic or Chinese astronomers, there's not much evidence that they did anything more than measure these cycles and identify the amount of time that they took and predict where Mars is going to be in 2 years, when the next solar eclipse is, when sunrise is going to be on a particular day of the year. It doesn't seem like many of these cultures made much of an attempt to explain why Mars moves in such and such a way, and the sun moves in such and such a way, and the moon moves in such and such a way, and how far away they are. And the process of creating not just a description or a prediction, but an explanation of why Mars goes around in such an amount of time and Jupiter goes around in such an amount of time is the difference between kind of descriptive observations and science. The creation of a theoretical model that explains the reason that things in the sky move the way they do will not happen historically until this time period that we call the scientific revolution, starting with, let's say, Copernicus in 1542, Galileo 1609, Isaac Newton 1687. That window in there, we make a leap from simply drawing a picture on a piece of paper to figure out where Mars is going to be at a certain day of the year, and actually having a quantitative, unifying, explanatory, scientific model that explains why the things in the sky move the way they do. So for us, in a modern scientific astronomy class, that is what is of interest. We're not going to spend a lot of time talking about constellations and how the planets move across the sky and the descriptive part of astronomy. We need to fast forward to the modern scientific theoretical explanations for why the things in the sky move the way they do. The earliest attempt at modeling what goes on in the sky looks something like this. What happens every night when you go out? Well, the sun rises in the east and sets in the west, and the moon rises and sets, and the stars all move in a circle around Polaris. And if you go outside and look up in the sky, it looks like everything is moving in a circle around the Earth. So the most obvious model for what the universe is like is the Earth's at the center, and then the moon, and then Mercury and Venus, and then the sun, and then Mars, and Jupiter, and Saturn, and all the stars all go around the Earth in these big circles. This is called a geocentric, Earth-centered model of the universe. And it was the prevailing way to think about the structure of the universe for thousands of years, because it is quite simply what it looks like when you go outside and you look up at the sky and you notice what's going on. Everything seems to move in some sort of cycle around our planet. We all know today that this is wrong. We all know that the Earth spins on its axis and the Earth goes around the sun, and we're not the center of the universe. But for thousands of years, this was the prevailing picture of how the universe was structured. What I want to talk about really, really briefly, because I don't want to stay kind of stuck in ancient astronomy for too long, in another video, is how we made the shift from this geocentric model, which has been around for thousands of years, to the modern picture, the heliocentric model, where the sun is the center of our solar system. The Earth and planets go around the sun, and it's the Earth spinning on its axis that makes everything look like it's going around us in a circle. That was a very difficult thing to demonstrate. And we owe that knowledge to Copernicus and Galileo and Newton, and we will talk about that in a later video.